2. This is the first lecture after exam 2, so it's time to get back in the routine. A couple things. Remember, homework is available, so chapter 9 is posted. This is definitely one of the more strange chapters that we'll have. So the homework's not very long, but the concepts here can be really difficult. So you'll spend, if you take Chem 200, even more detail on electrons, but we'll introduce electrons and all the understanding kind of at the beginning, what we're going to do, and then we'll do some applications of it at the end, which I think will be really helpful. Please see me during office hours if you'd like to go over problems, concepts, quiz, exam. That'll take a little time for me to get back to you, but look at this routine, okay? This is the way CHEM152 is even before this transition online. These regular quizzes to keep up with the material. So quiz 4, April 16th, and then quiz 5, April 23rd. The withdrawal date is May 8th. If you've got questions about that, please let me know, and we will revisit the class theme as we start up getting ready for exam 3. So all chapter here will be discussed in this video, and like I said, the conceptual is very difficult at times, and then we'll get to this practical. How does this help us? What are we going to do with this? Okay. The good news is you have one video, chapter 9, and that's 2 days that you get to work on that video, and then this quiz is just a chapter 9 quiz, so that should help in getting ready for that. Our class theme, remember, the Olympics. So after coming off an exam, it's really important to recover. What does that mean to recover? Listen to yourself, take breaks. This is a very strange time. It's hard to adjust, but definitely do what it takes to get into a routine, to get back to recovery, because you need to start back at studying. These concepts build for sure. It's really important to keep at it. So chapter 9, it's all about the electrons, and like I said, we'll eventually get to how this connects to the periodic table, so I don't think you'll look at the periodic table quite the same again after all of this. So, for sure in chemistry, if we're talking about chemical reactions, we're all about the electrons, okay? What's going on with these electrons? Are they shared? Are they lost? Are they gained? What's happening? That's a really important part of chemical reactions. And where are these electrons? How are they organized? Okay, we talked before about elements having protons, neutrons, electrons. We know the electrons are outside the nucleus. Now we're really going to get to the big picture of what does this look like. I already mentioned the reactions, so this reactivity, we're going to see how that relates to the periodic table. And it's definitely all about the electrons. As I mentioned, Chem 200 spend a lot more time going over these topics, but some of the greatest scientists known studied these electrons, and it is bizarre, very bizarre, and some of them didn't even really like it. Einstein, I don't like it, and I'm sorry I've ever had anything to do with it. Or Einstein said, God does not play dice with the universe. So this is about probability, okay? We are not going to be able to say we know exactly where an electron is, but we are going to talk about probability. Where is it most likely to be found? So that's an important concept when we think about electrons. But what's pretty typical is before we get to electrons, we talk about light, okay? So what is light? It can interact with atoms. This was known at the time, so they're studying those interactions. And this understanding of light helps understanding of electrons. So light is called electromagnetic radiation. Just sounds impressive saying it that way. And light travels at a speed of 3 × 10⁸ meters per second. So that is equivalent to the speed of light. And in Chem 200 you do a lot more calculations. So you need to know that speed of light and use that speed of light. Here we talk more conceptually about that. So light is a wave. It's considered, you can see here, coming out just like our liquid water gives out waves. light gives out waves as well. So classical wave, but that wasn't exactly a great description. But what do we mean for waves? Some of you may surf, some of you may have a good understanding of this. Well, there's wavelength. That can describe a wave. Distance here. So wavelength is distance. Frequency is how often, so how number of waves per time. And I mentioned earlier the speed of light. That's the relationship between frequency and wavelength. That's the speed of light equals frequency times wavelength. So you can imagine then if I had a shorter wavelength, then I'd have a greater frequency. So these are inverse related. Wavelength goes down, frequency goes up. If you have a longer wavelength, that goes up, this goes down. So those are inverse related. Light can also be separated. We've got a prism here that can separate light out into its different colors. We've got the wavelength, frequency. I already mentioned the inverse relationship, so that's here, they're vice versa. And said light is a wave. Well, guess what? It's also a particle. So this was Einstein working on this, and this is called principle of duality. It is both. Light is a wave, light is a particle. So what that means is there are some very interesting experiments that led to the idea that light comes as particles or packets. Those are called photons. So if you're under this light, then you're being showered with light particles. So that's seeing both is really key. Light is a wave, light is a particle, because we're going to see the same thing with electrons. Electrons are waves, electrons are particles. So the electromagnetic spectrum here, wanted to point out a few things. First, you can see the energy. Okay, so energy high, energy low. So if you look here then, you can see that that's a very long wavelength for low energy. That's a very short wavelength for high energy, which also means that's a high frequency, low frequency. And you know some of this, right? So you know X-rays, you don't stand in front of an X-ray machine all day. That would be a problem. So that has higher energy. Maybe you've heard of gamma ray guns, or we definitely know not to go outside without protecting from the UV rays. Maybe you're also familiar that radio waves are all around us, but we don't worry about those. That's okay. We're not too worried because it's low energy. Microwaves, infrared also fall on the low energy scale. So the light we actually see, you can see, is a very, very small portion. 400 to 750 nanometers is what we're seeing there. So atoms, chemistry, we're looking at elements. We looked at ions, different things. Well, atoms can emit light, okay? So this is an experiment that you'll do in CHEM152Ch9, is you'll look at an element inside a tube. It's charged with electricity and it emits different colors of light. Maybe you've seen this before, neon lights, but this is what's happening for a range of elements, and they have distinct colors. Well, those distinct colors are from specific energy levels. So if you look here for hydrogen, you can see that it has 4 lines, and those coincide with energy levels that change. So at times you're going to see energy levels listed like this, and what we're going to do, make the transition to the idea of talking about electrons. Well, if an electron is in the first energy level, it can get excited and move to the second energy level. Well, it can't reside in that excited state. It has to relax back down, and when it relaxes back down, it gives off light. So this can happen in lots of different transitions. In CHEM152Ch9, you look at these transitions for hydrogen, these 4, and determine specifically which transitions are happening. You can see, obviously, it gets more and more complicated. Helium and neon, the more and more transitions that can happen, the more lines. But this is very distinct for these elements. You can identify hydrogen by this pattern and helium by this pattern. So these are called atomic line spectra. And Bohr, famous scientist, looked at this and was not just satisfied with saying, wow, that's impressive, but he did a calculation. What's an equation that can relate these lines, where these lines are located and how many lines. So it was really interesting how he could apply this to that known atomic line spectra. So as I showed, it's the movement of electrons. Those are emit light, but why lines? Okay, so I showed you there are specific energy levels, so that's why there's specific lines that can come out. So Bohr's response to this then was to create a model that showed, well, just like planets have orbits, so we have a nucleus, there's orbits around the nucleus where these electrons are. Okay, so they only have certain energy. So this is called quantum chemistry, or quantized, because it's specific energy levels. It's not a 3.4 or 4.1. They're distinct energy levels. And it's weird. This is what the scientists to start with were so strange. Like, it doesn't make sense. It's so bizarre, because it's like saying you can only have certain increments here. It just doesn't seem to make sense. So Bohr, you can see, as earlier I drew something similar to this. There's different energy levels, and you can see they're not the same length separating these energy levels. So the higher you go in energy, the closer they are to each other. But just like if you fell off the top step, n equals 6, you would be hurting a lot more than if you fell off at the first one. Okay, so this is much higher in energy, much lower in energy. Of course, you can't stand at here or here or here. This is the idea of quantum chemistry. There are specific areas that you can be at. So Bohr's model then specified the quantum number, okay, n, and if you move to a higher orbit, that takes energy, so you must absorb. And if you move to a lower energy, then you're emitting energy. So that's where that light came from. So this is another diagram to show this. There's a lot going on here, but wanting to point out excitation, remember, is taking in energy, absorbing energy. So it's going from the first energy level, and it's going here to this energy level. Relaxation, it's in the fourth energy level, and it goes down to the third energy level, so it emits, it gives off light. So hydrogen then, got examples here. The 3 lines that are listed here are the red, the blue, green, and the violet. They're coming from energy level 4 going to energy level 2. Energy level 3 going to energy level 2, energy level 5 going to energy level 2. So those are these color transitions for hydrogen. So Bohr had this amazing breakthrough. It explained hydrogen so well, everything's looking great, and it only works for hydrogen. Okay, so there's some problems there then. It didn't work when it was extended to everything else. Okay, so if you look at the 118 plus elements, just one, that's not exactly what we're going for a model. So the new model was developed that works for all atoms, and that's what we're going to talk about here. So it goes back to electrons, and electrons being like light, being waves and particles. So if you treat that, then electrons can be in and out of phase like waves. Okay, well, that means we don't know exactly where they are. So what we're going to do is see that the best you can do is come up with probability maps. So you don't know exactly where an electron is, but you can see where it is most likely to be. That's what we're going to be seeing with electrons. So what this means is, you know, we can predict exactly where the baseball is for the most part. If you're watching a game, if it's hit, is it going to go out? Maybe it's not. So you can focus on that because that's the big scale, the macro scale. The micro scale, electrons, we can't do that. Okay, what we can only do is the probability map. Okay, so what's going on here is that more than likely the pitcher is going to throw a strike. Okay, well, there's actually some probability they're going to be outside the strike zone. There's actually a probability it could be up against the wall here or out into the stands. Like, that's possible, but the probability map is showing where is the ball most likely to go. Okay, so that's what we're talking about here with electrons. So what that is an orbital. Okay, this is very different than an orbit. Remember, nucleus, an orbit, you can say there's the electron right there. It's going to rotate around, and we can predict where it's going to be. We know exactly where it's at. That is not electrons. Okay, electrons are, we have this region. Okay, it looks very similar to this, but I'm trying to draw a sphere here. We have this region of where an electron is most likely to be found. Okay, that's an orbital. That's different than orbits. So that's a probability map. Okay, so I just drew a simple one here of a sphere of a probability map, but it definitely gets more complicated as we go on. So orbitals, the Bohr model had one quantum number, that was that n. Orbitals have 4 quantum numbers, and you'll go in great detail about that in CHEM152Ch9. We just talk a little bit about quantum numbers here. Orbitals, because they're so complex, they're waves. They're probability maps based on waves. And we can see there's 2 quantum numbers we're going to talk about. Principal quantum number, just like Bohr, that was n. So that's the size. How big is it? And what is the shape of it? That's the subshell. Okay. The shapes are S, P, D, F. That's what we'll talk about for the shapes. So principal quantum number n equals 1, 2, 3, 4, and so on. That is the size. That is how far away from the nucleus. That's the principal quantum number, or the principal shell of the orbital. So of course, as I mentioned earlier, the higher the number, the greater the energy, and the farther away from the nucleus. Subshells, a little more complicated. They have different shapes. Okay, remember these shapes, what we're talking about, the translation should be probability. Where is the likelihood of these electrons? These are probabilities. Okay, so the shapes, S, P, D, F, and we're going to talk about those shapes, and you can see the shapes matching up to the shell. So n equals 1 only has S, n equals 2 only has S and P, and then we add 1 at each energy level there. So the S, I already drew this a little bit, you can see it's a sphere. So the likelihood the electron is going to be somewhere in this sphere, that's S, that's the spherical orbital. That's the lowest energy and what we call the ground state. So you can have a 1s, then you can have a 2s. You can see the shape is the same, but it has higher energy, it's farther away from the nucleus. You could transition from the 1s to the 2s by the excited state. So that's maybe what you've seen before, and especially what we think about atoms as spheres. That's a sphere, that's a bigger sphere. Well, we have different shapes. The p orbitals, okay? Okay, so there's 3 p orbitals, px, py, and pz, and you can see they're bilobed. Okay, what that means is that region here and here is the probability of where that electron can be found in the p orbital. Same thing here in these orbitals. So this shape looks different, and the shapes get even more complicated. Look at the d orbitals, even more. But the real take home, not asking you to draw shapes or memorize, what this, even the name of the orbital is. Just you're being asked to understand that this is the likelihood of where electrons are going to be found. And we're going to get to how this helps us in chemistry. Okay, so the order of orbitals is going to be really helpful. In this diagram, you can see has a lot of information. The S's increase up. You see how the P's have 3 orbitals each. The D's have 5 orbitals each. You're going to actually get this information from the periodic table, so you don't have to commit this to memory. I'll show you the pattern how you can get this from just looking at the periodic table. We're going to draw electrons as either an arrow up, an arrow down. This is the spin. So some terminology. We can see that the Pauli exclusion exclusion principle, only 2 electrons of opposite spin, you see how I'm matching those up, can occupy an orbital. Okay, so this is going to help us in Tool later when we talk about where these electrons are. So we're going to use electron configuration. It's going to be a very practical skill, and an orbital diagram, and that helps us predict where these electrons are going to be. So let's start with hydrogen. Simplest, maybe you've seen this before, this terminology. This we would say is 1s1, okay? So this number 1 is the principal quantum number, n, okay? The s, remember, is the shape, and that's the number of electrons. So 1s1 has the principal quantum number of 1, so it's the first energy level, and it's in the spherical shape, and there's 1 electron there. And this is the orbital diagram. We have a box, and there's 1 electron, and it's customary to write the electron facing up. Another diagram to memorize these electron configurations is if you wrote 1s, 2s all the way down, and then you see how the 2s is next to the 2p, 3s, 3p, 3d, and so on. You are looking at the order of how you fill. But remember, we're going to get the periodic table. You will always have the periodic table. You can get this same order from the periodic table. Another rule, so we had Pauli exclusion principle. Another rule is Hund's rule. There are only 2 electrons with opposite spin per orbital. And what happens if there's more than 1 orbital available? So this is talking about orbitals other than s. So if we have carbon, for instance, the s pairs up, that's the lowest energy. 2s pairs up because that's the second lowest in energy. And then 2p is a little higher in energy. But look how we've got 3 orbitals in 2p, and they all have the same energy. So these 2 electrons then, you want to spread them out and give them their space. It's like renting an apartment in San Diego. There's no way you would pair up and share 1 room and have 2 empty rooms. You definitely want your own space. That's the same for electrons. So remember, these arrows are negative numbers, okay? So they're negative charges, so they're repelling each other, so we want to give them their space, okay? So if you look at the periodic table then, this is how we can get the electron configuration from carbon. If you look at the periodic table, you go from left to right. Hydrogen we already saw was 1s1. If you keep going right, that's helium, that's 1s2. Then you go down to lithium, that's 2s1, 2s2. So I'm writing the outermost electrons here just so you can see the pattern of the electrons are filling boron 2p1, and now you can see carbon, it fills all of those. So 1s2 filled, 2s2 filled, and then 2p2s are outer ones there. So we want to work left to right on the periodic table, and I'll give a couple examples here. Magnesium, sulfur, gallium, so take a couple minutes, pause this, and write out the electron configuration. What you can see from looking at the periodic table is that magnesium is on period 3, So we already went through carbon, and that got us from 1s2, 2s2, and then the carbon period is filled. That's 2p6. So that takes us to the next level, which was 3s2. Then we just continue on with sulfur, and that would be 3p4. And if you can continue on, we just add, and that gets us to 4p1. So a couple things to double check. Magnesium, if you look, that's 12 protons. And if you look here, there's no charge. So these numbers, 2, 4, plus 6 is 10, plus 2, that's 12 electrons. So you can always double check, do I have the right number of protons, right number of electrons? So sulfur should have 16, and then we can see gallium has 31. So this is what I want to emphasize. The blocks on the periodic table, that's what you need to use. Okay, so the periodic table is organized by this S, P, D, and F. You can look at that, use that, and I'll show how we can see that in the next slide. And it's always nice when you see this. It allows you to easily do this. Well, I think with time you can see using the periodic table, I think it will come with time. You can see where's the S block, where's the P block, and so on. The orbital diagrams we'll use to see are the electrons paired, are they spread out? We'll do that. And look at the periodic table, the S, it can remind you only 2 electrons go in S, 6 go in P, 10 go in D, 14 go in F. So all of those are there for you. So what I was saying earlier, it's hard to visualize now. You can see it a little bit better. You take the question, what's the electron configuration for arsenic? And you can work through. This is the S block. This is the P block. This is the D block. Okay. There's also a shorthand or noble gas configuration. You can go here and say, well, I've got the electron configuration up to argon. Then I go 4s2. I'm working left to right. Then that goes 3d10. And I'm not finished yet. That's 4p3. That's the electron configuration for arsenic. So we've got a lot of electrons we're talking about, but let's distinguish between the two types of electrons. Okay, so we've got core electrons and we've got valence electrons. So core are not the outermost, valence are the outermost. These are going to be the ones that are for bonding, valence electrons. And we can look at this by getting our electron configuration and see, remember the principal quantum number n, those are the outermost. So n equals 4, outermost, that's 6 valence electrons. All the rest for selenium are less than 4, energy level 4, so that's core electrons. Valence electrons are going to tell us so much about reactivity, so it's really important to be able to distinguish which ones are valence electrons from the core electrons. They are the furthest out, that's the highest energy level. So they're the furthest out, they're the easiest to be lost or gained or react. All of that is what's happening with valence electrons. So now we get back to the periodic table and we can see, look at this pattern. The vertical group has the same number of valence electrons. And we're going to see they have a very similar chemistry. So it's all about the valence electrons in determining chemistry. So you can see here the one exception, helium, that's got 2 valence electrons. All the other noble gases have 8 valence electrons. So this periodic table is a little bit overwhelming, but the main thing is to see this pattern of filling left to right, 1s1, 1s2. You can get lots of electron configurations for the elements. There are some exceptions. CHEM152Ch9, we go in great detail about these exceptions that don't quite follow the pattern. But for this class, just want you to see how to write electron configurations and be aware how it's going to help us. So let's look at some more patterns. Noble gases. Everyone wants to be like the noble gases. You can see 8, special octet. These are 7, so it's just 1 away from the noble gases. Now we can see why they want to gain an electron to get to this noble gas configuration. If we look here, alkali metals, they're just 1 away. Okay, so if you look at sodium, it has 11 protons, 11 electrons. It's actually just 1 away from neon, which has 10 protons, 10 electrons. So you can see it can give away this 3s1, and then it's left with this electron configuration. So that's why these are +1 cations. So some trends from understanding the electron configuration can really help us predict what's going on with this periodic table. And that can be size, ionization energy, metallic character. So how is this going to help us? Well, if we think about shells, subshells, so energy level 1, energy level 2, you can, for sure, we already saw, if we're energy level 2, energy level 3, the more shells you have, the larger the size. Okay, so that's increasing the more that we have for the principal quantum number. Subshells, that's the 2s, 2p, they rest inside of a shell, so we're not adding any thickness. It's still that energy level 2. So as we go across a period, we're adding electrons and protons. Okay, so we go down the periodic table, this gets bigger. If we go across the periodic table, this actually gets smaller. Okay, we're adding these protons are attracting it in, pulling in the size. So this helps with the trend. If we take a look here, we can see definitely gets bigger as you go down. We can see it gets smaller as you go across. So that's the size trend on the periodic table. And explanation, okay, atomic size must increase, of course. We said the shells are increasing. If we're just filling the subshells, we're not increasing the size of the shell like we did up here, but we're also adding protons, so of course that pulls everything closer to it. So that's the atomic size trend. Another trend is ionization energy. So the definition is sodium gets ionized because energy is being added to remove. So this takes energy and an electron is being removed. So this follows a nice trend as well. I really encourage you to think about the size. Okay, remember, size gets bigger down and it gets bigger to the left. Well, if we're talking about size, we're saying the electron is much farther away from the nucleus. So if it's much farther away, it's not as attracted, it's easier to remove. Okay, so that's what we're going to be seeing with ionization energy. So if you take a look here, ionization energy trend, look at this, it decreases as you go down because this electron is much farther out for francium than it is for sodium. So the electron is held more tightly with sodium. The nucleus is so far away, this electron isn't attracted as much. Remember, we go here, that's smaller, so this electron is much more difficult to remove, so ionization energy increases. That's the trend, ionization energy, and of course, I really encourage you to think about this together with size. If it's farther away, it's easier to remove. The larger atoms will have lower ionization because the electrons are farther out. So that's smaller atoms, the electron is closer together, that's more difficult to remove. The last trend that we're going to look at is metallic character. And one thing to note is that metals like to give away electrons. Okay, so really this is a trend we've already looked at. This is ionization energy. Okay, so if metals want to lose electrons, that makes them metals, that makes them who they are, then we just need to know the ionization energies. If we know that trend, we know the metallic character trend. So that's the opposite ionization energy. Remember, so metals really want to do this. They really, really want to give up an electron, so the ionization needs to be low. It should be easy to give up an electron. So let's take a look, okay? Well, think about what you do know. Metals are on the left side of the periodic table. Non-metals are on the right side. So you don't even have to know anything about this chapter to know, oh yeah, if I go right, the metallic character is decreasing. Okay, we'll actually look at group 15 here. If you go down, you start at non-metals, you go through metalloids, and you end up with metals. So that also affirms this metallic character increases trend. So with all of these then, you should be able to look whether it's size, ionization energy, or metallic character. Look at the periodic table, find these elements, and circle the appropriate one. So go ahead and take a look. If you look here, lead would be a larger atom than polonium, and selenium would be larger than chlorine. Selenium's down and to the left. That follows increasing shells. That would be a bigger size. A higher ionization energy. Magnesium and strontium are both group 2, but strontium's bigger. Okay, if strontium's bigger, it's easy to remove an electron. Magnesium's smaller, it's more difficult. Copper's a metal, it wants to lose an electron. Phosphorus is a non-metal. Both of these are metals. It's kind of a strange question, right? Well, which one is more of a metal? Gold or copper? Well, the metallic character increases down, so that would be gold. And then both of these, this feels like an even stranger question, are non-metals, but silicon is more metallic. It's down and to the left. So that concludes this chapter 9. Again, there's a lot of concepts here. The homework's not very long, but I really encourage you, read, come to office hours, talk about these concepts, because there's a lot going on here, and then there's some practical applications at the end.